Well, thank you. Thank you for coming to the session. So this talk, we've heard a lot about how we can find fuels or find raw materials for fuels, and we've had a really good introduction into the market size. So what we're talking about here is how you prepare those raw fuels, the raw oils, for hydrogenation. So we've heard a good point about how there's three main fuels that we're talking about here are biodiesel, renewable diesel, and SAF. Renewable diesel and SAF are produced with hydrogenation, and that requires a very clean raw material. So what we have done is we have applied a technique called microfluidics into trying to clean up oils and other things. And I want to give a few minutes into microfluidics because not everyone probably is aware of what that is. After this talk, if you have interest, I encourage you to look into some literature. It's a really fascinating field. You may know of microfluidics as lab on a chip or as an inkjet printer. It is the control of micro volumes of liquids into some application. In this application right here we have drawn is a true microfluidic device, and it was created by taking two pieces of plastic and chiseling a Y into one of the pieces of plastic and then gluing another piece of plastic on top of it. So we created a channel where, in this example, we're mixing a yellow liquid with a blue liquid. You can see them coming in, see them coming through the channel, mixing, and it's really hard to see, but this turns green, which is what you would expect when you mix those two colors together. This microfluidic device has very unique properties in that one of the really big advantages of microfluidics is we have very little mixing, very little turbulence. The fluids are so thin that you basically can get laminar flow at rates that are unusually high. So one property is laminar flow. The two liquids can actually slide by each other through that channel and not actually mix, but they have diffusional barriers. The diffusion happens at the surface, but the surfaces don't really interact very much other than diffusion. So what we've done is we've taken the idea of microfluidics and scaled it up into something that is scalable into industrial size. So you can imagine trying to scale this device, which probably processes 500 milliliters a minute, 500 microliters a minute, into hundreds of gallons a minute. It's not a practical way to do it, which is why it's been used for lab on a chip and inkjet printers, other things that very small volumes are what we're working with. But there's a need in the industry to do other things. So we have taken advantage of this microfluidic property, and we have scaled that up into massive microchannel reactors. We've done that by taking wires or fibers and put them very close together where we can control the distance between the fibers such that they mimic the lengths that are found in microfluidic devices. So we can have channels of virtually any width we would like. 50 micrometers is a really common number. So once we do this and we can pack these fibers in, we now have the ability to pack more and more fibers into an increasingly larger device. So we end up here building different columns that have different lengths and different diameters, and now we're into the gallons a minute, tens of gallons a minute, and hundreds of gallons a minute type of processing flow using the advantage and the interesting properties of microfluidic devices. So some of the things that happen when we go through this process is the surface area becomes exceedingly high. We have up to 50,000 meters squared per cubic meter of surface area because we have all these very small fibers packed in this reactor to whatever density we need. We have very rapid mass transfer because the diffusional barriers between these 50 micrometer thin ribbons of, we'll say, oil, water, there's very, very little diffusional barrier. They're very, very thin. We have huge surface area contact, so we get great mass transfer in the system. Hydrodynamics, generally these systems operate in laminar flow, which means if you have two fluids that are immiscible, oil and water, flowing by each other, they don't mix up and cause emulsions. They just slide down together and they touch at the interface, and mass transfer occurs at that touch. But we don't get this turbulence. We can also operate it in droplet flow matter, where we end up with droplets that follow each other. And it's also possible to do turbulent flow, but that's not a very common method. But one thing that is really interesting about how this happens is now you can see we can scale this to virtually any size the industry might need. It's no longer a piece of plastic chiseled with a micrometer size hole and you make millions of them. You build one reactor that has whatever packing you need. Lastly, what we have been able to do, and there's a second talk if you want to think about this, in the second biofuels area, we've been able to modify the surface of the fibers. So normally we are talking about the microfluidic reactor as if it's a reactor. It's two walls and something happens inside. We have now been able to change the walls to make the walls participate in the reaction. We're able to put catalysts on the walls and other things on the walls of these little reactor. So now it is more than just a vessel. It is a vessel that has attributes that can help with the reaction in some sense. So one of the big advantages of fiber reactors or microfluidic devices like this is the pressure drop is very low. So we have here a normal packed bed column that is 50 micrometer diameter silica beads, a common packed bed you'd see for all kinds of things. And we did some math and said, okay, if it's about a meter tall and about 25 millimeters in diameter, and we start raising the rate from 0 milliliters a minute up to 1,000, the pressure linearly increases up to about nearly 400 psi. It increases because the liquids have to work their way through all these little balls of silica, and a tortuous path creates a lot of back pressure. But when we do the same exact flow in a microfluidic fiber reactor, the pressure drop is not 200 psi, it's 1.2 psi, or 2.4 psi when it's 360. That's because we have these channels that go all the way through. So the liquids can follow a highway all the way from top to bottom and don't have to go through all these barriers to get there. So even using the same size fibers as the silica beads, the pressure drop is very low and the throughput then can be very high. So here's an example of how we do it, and this is actually a fiber reactor, lab version, and it's packed full of fibers, and we're mixing two fluids together. One is dyed yellow, and one is dyed blue. Blue is a water-based material, and yellow is an oil-based material. And it's getting a little hard to see, but they're flowing through here. You can kind of see some bubbles. It makes it easier to see. And over here is how you do it with a stirred tank reactor, the same exact fluids. So if you put it in a stirred tank and you stir it all up, one, you have energy to stir it. Two, it takes time to get it going. And three, you get all this energy in here. And now when you stop, you have all these bubbles, emulsions and so forth that you don't want. So you have to wait for that to all collapse because you've done this dispersive mixing and agitation. For a fiber reactor, we don't get that. It's laminar flow. We don't have this high mixing. So we really don't form emulsions. So since we don't form them, they don't have to be removed later through a big settling vessel. It's very small footprint, and there's no energy to do this. You just pump it through. The pressure drop, as we just went through, is very, very small. So it's just the energy to pump the liquids through the column, as opposed to the energy for an agitator to stir the material and force that contact through mechanical energy. So we already heard a little bit about the market for renewable diesel. I'm not going to cover that. And we also heard a little bit about hydrogenation. So I can kind of skip through that. But just really quickly, most of you have vegetable oil experience. I'm expecting a lot of you have been in food. Hydrogenation of vegetable oils, we do a lot. And in that process, we use a nickel or platinum catalyst, but generally we have a finely dispersed marine nickel that we pour in at a very small concentration into a reactor with oil, pump hydrogen through it, and we do our reaction. And then at the end, we filter the nickel out and throw it away. In renewable diesel, that's not how they do it. They have a catalyst that's fixed on a solid bed that has to last for 1 to 4 years. Otherwise, the economics fall apart. It's a very expensive catalyst. The issue is that catalyst is poisoned just like the nickel or platinum would be if you're making vegetable oil for food. That same poisoning happens where all the metals, phosphorus and chlorides in particular, will poison that catalyst over time. And they will basically destroy the catalyst's ability to function. So that catalyst is supposed to last 3 years, may last a year or a half year or 3 months or 3 weeks at times. So it's a real big problem to get all that oil, all those contaminants out of the oil. What the industry has been using to start up is RBD soybean oil. That's really the gold standard. That's a food-grade oil. We've done through all the processing. It is really clean oil. The problem is, as we just heard, the carbon intensity of that isn't great. It's bad. So we want to get lower carbon intensity. And so we need to clean up all the oils we use need to be cleaned up. Soybeans already been cleaned up with RBD. It's an expensive process, but it works. And we already saw the market share of these oils, and as we heard, soybean is disfavored because it has this high CI value, and the other ones are trying to take over. So what we did was we went after DCO, or corn oil, and we heard that's the oil taken out of distillers' residues, or fermentation residues. Today, there's about 600 million gallons of that produced. It has a CI score that's about half of that of soybean oil. It is increasing over time. We're expecting by 2026 or so to have 800 million gallons produced, not because we are necessarily using more grain, but because the extraction techniques are getting better over time to remove it from the grains. So DCO is a meaningful, large volume raw material that has low CI score that is very amenable to hydrogenation to make diesels and jet fuels. So this is how we actually do it in the field. We built this as a cartoon, but we have a fiber reactor that has a reactor section, and then it has a gravity separator on the bottom. And if I zoom in here into look at two fibers, I got fiber 1, and I got its neighbor next to it. Between those two fibers, there's the void. That's the microchannel. And we can make the microchannel thicker or narrower or wider based on the fibers we use, how many we put in, the size, and a few other things. But we have this microchannel between the two fibers. And now when we put, in this case, oil and water through, the water and oil will not mix together. They will slide down the surface with laminar flow. But we have this contact point where the yellow oil and the blue water contact, and it allows for diffusion of materials that are soluble in one or the other. So in this application, I have a bunch of little white dots here that I'm representing as a water-soluble, or at least somewhat water-soluble contaminant that's in the oil. And as the oil and the water slide down, the contaminants will dissolve into the water, leaving the oil clean, and as it transmits the entire length of the reactor, comes down here, and now all the contaminants have washed out of the oil into the water, and now we let any little emulsion that did form, we let separate. We pull the oil out that's clean and ready to go for its next process, and any contaminants come out in the aqueous phase. Generally, we are getting very little emulsion because we have laminar flow. We don't have any moving parts, as I mentioned before. And in this application, we're basically getting between 75 and 85% of the contaminants removed in a single pass. Generally, we're getting the oil below 3 ppm phosphorus and below 10 ppm total metals, which is the latest spec we've been given by renewable diesel plants, although that has moved down over time. And we've been able to adapt the technology to make it better as needed. So here's some examples. Just for time's sake, I don't want to just look at two of these. One showing the phosphorus removal in a step. It started at 370 ppm. This actually wasn't DCO, but it was a similar oil. And after the first wash, we took the phosphorus from 370 down to 9.1. Wash 2, 8.4, wash 3, 8.4. Meaning we basically got everything that was water soluble on the first shot. Doing more and more didn't really help. FFA, we had a similar thing where we started at 13.5% FFA. We got 10.5 left in the oil after the first wash, and further washes didn't change that. This is important because this means that most of the oils are kept in the oil. There's very little yield loss into the water phase. So here's some actual results using this oil. And we came in here, I'm just going to go to the bottom here. This particular crude 1, had 73 parts per million total metals. And of the two that are really interesting, phosphorus and potassium. And we took that down to 7.9 on a single pass. So it's about 89% recovery. Crude 2 was cleaner, 51 starting material, and 9.3 after one wash. Crude 3 was cleaner yet, about 30 ppm starting, 6.9 finishing, and crude 4 was the cleanest we saw, 15.3 start and 3.1 end. And the important point is that the RD and SIF producers want that number today be below 10. So all these cases, a single pass got us below 10. We've also processed more difficult oils that start higher. So if we go back here, this one started at 73 parts per million. The second set started at 650 parts per million. First pass took it down to 16. We washed it a second time, got down to 3.6. Crude number 2 started over 1,000 ppm. We got down to 44 on pass 1 and 10.7 on pass 2. Crude 3 was the 170 starting, 28 pass 1 and 8.9 pass 2. So even if the oil is really dirty, it is possible to take care of this with a water wash. So these things are commercially deployed. We have 2 commercial deployments right now. They've been running both for a little over a year, almost 2 years. And there's 2 scales. One is a 5-gallon-a-minute system, 5 gallons a minute of oil. The other is 16 gallons a minute of oil. And in both cases, they commercially produce oil that's below 7 ppm total metals, and generally we can get down the phosphorus below to 1.5 ppm. What's interesting about this, which is different than RBD soy or most of the techniques that we talk about for cleaning up oils, is we don't use any solid absorbents. There's no bleaching clay, no silica, no diatomaceous earth, nothing. This entire process is done with RO water. That's the only ingredient. So that, if those of you that are in the space of dealing with these clays, it is a problem. It's a problem because you got to buy them. It's a problem because they lose yield because the clays absorb some of the oil that you don't want to have absorbed. And then maybe the biggest problem is you got to dispose of the stuff. And that's not always easy. But this is just water. We had very little yield loss. And the other part about this at an ethanol plant is even if we have some yield loss into the water phase, that water isn't thrown to a wastewater treatment. That water runs back to the front of the plant for more fermentation, so the oil that is in there gets another shot. So we don't actually lose it then either. It's a very low OPEX cost because we're just using RO water. The OPEX to run this thing is very little energy. OPEX is less than a half penny a pound to pre-treat the oil. As I mentioned, the impurities go back to the ethanol plant as part of the distillers, so there's really no waste disposal cost at all, which is why one of the reasons the operating cost is as low as it is. Here's a picture of the system that we've installed in these 2 places. It's about 3 meters long. It's about half a meter in diameter as a column, and the column length is a little under 2 meters in active surface area. And this is a sight window on the end of the reactor, and you can see in a sight window, we can see that there's a definite phase of the oil up top and water on the bottom. So we can use the sight glass to see, is there any emulsion forming, and do we need to make adjustments to make it work better or not? And so right now we've been using, almost all the applications have been with steel. 304L is what we've been using, but there are literally hundreds of materials that can be drawn into fibers that we can modify and put into these reactors. 316L, Hastelloys, polymers of various types, other materials, copper, volcanic glass, carbon fibers. There's just a whole bunch of fibers that you can buy and have tailored to whatever size that might be needed to get the job done. The magic really is how we do the internal packing. So I made it sound like it's just simple, straight things. It's easy. There's more behind that we haven't disclosed, but it does work really well. And we can adjust that matrix and all the fibers and a bunch of little things to choose and produce a material that's needed. And these systems are basically built for purpose. We don't have, it's not like a toaster where you just go buy any toaster. We make a toaster for the bagel you have. It's the right size. And a separator also has some interesting points about it to separate that water from the oil. And this is application, what I'm talking about here is DCO, but we have other applications that are of interest that we've used. Thank you for your time. I encourage you, if you have time, next session, you're going to hear a better version of this because you're going to, Leslie Wood, one of my colleagues, is going to talk about how we have immobilized enzymes on the fiber and what that did for pretreatment. Thank you.